So these are basically the joints of these bars that we have. So let's just color it so that we can make the differentiation. These are in black. That's a different body, so let's make it in a different color. Okay, so these are the three portions, and we have hinge joints at all these positions. Now what is the meaning of hinge joint? It means that there will be no translational motion, but there can be a moment, you know. So what it means is that at this point it can actually go down and up. I mean, it can rotate, but it cannot. But this point cannot move anywhere in X and Y direction. So it's like a hinge. I hope you know what hinge is. Now let's replace these hinge with reaction forces. So these basically are the reactions that are acting at these points. Now since they were hinged, I replaced that with two translational reaction, so that this portion of the beam does not move, and in the X and Y direction, and but there is a possibility of it rotating in these directions like that, and therefore there is no reaction moment that is holding it up, you know. At this portion, you know, it is a tricky job to find out what the reactions would be. I know that this is a hinged portion, the joints are hinged, but it is always, you know, we make mistakes of making, because it is a hinge, there will be translational reaction there. We always put a reaction column like that. It can work actually. If you put this into equations, you will end up getting one of the reactions 0 if it is 0. But at this position, it is always good. It's always a good practice to try to find out what exactly the reaction will be. Okay, so as you can see, I have drawn this portion over here. What I'm trying to project here is that if these positions are hinged, if that is hinged, and this is also hinged, in order to find the reaction which is acting at this point, let's replace this bar, take away this bar. We don't need that at this moment, and we'll see what is the force, or what is the direction of the forces that will hold this bar at this point. So it is always a good, you know, sometimes it actually works that you replace the joints with yourself. Let me draw that to make it more clear. So here it goes. For example, this particular portion of the bar is that portion, and the end of it, in place of the joint, you are hanging and you have been restrained at this position so that you don't move down or up, and there's no force acting in you other than the forces that this bar would apply. So initially imagine that this L bar is in this position and is well supported at this point, hinged. Now you pull it backwards in this direction, and so that your hands can reach you, and this is the blue one is the new position of the bar, and you're somehow holding it like that. Now if you apply a force which is acting downwards, what will happen? It will try to create a moment in this direction, and because of that you will experience a force only in that direction, right? Because this bar, the blue one, will try to go to the position of black and will try to move in this direction, and the only force that you will experience is the horizontal force, and therefore at this position the reaction will only be a horizontal one, not a vertical reaction. Although it is a hinge joint, and you can replace the hinge joint with vertical and horizontal translational reactions, but at this position you can easily find that we don't really have a translational reaction in the Y direction. So we know that at that point the only reaction we have is in the opposite direction. We still don't have the values of it, so we don't know whether it's positive or negative, but logically you can see that it is moving the opposite direction, so it will be in the negative direction of the x-axis. Okay, so we know the direction at that point. What about this? Since this is the fulcrum, this is the point at which it is supported, there will definitely be a force that is pushing the bar at the position where it is. Okay, so there is one reaction. What about the transitional reaction? Okay, we don't know that. So now in order to find the reactions at that point, we take out this bar. We forget about this bar now. Okay, and then we place this guy holding this L-shaped bar over here. Now considering just the blue one. Okay, now if he's holding it like that, what will happen if we apply a 600 force downwards? This portion will move up, not in that way, but this way. So we'll try to rotate here, and we'll try to rotate here in this direction, and the new position would be something like that. But in equilibrium position, nothing like this is happening, because this has to be very stiff. It cannot move around. Therefore, we now know that there must be a force which is pushing this bar backwards in that direction, and therefore we must have a force in this direction acting, right? So we have all the reactions at all the points. We know that one of the reaction forces is acting in the horizontal direction, the other would be acting here in the horizontal, but in the opposite direction. We don't know the direction. We'll assume that we don't know the direction, but just for the sake of understanding, we'll write it down. Okay, so let me clear it up. Okay, there you go. I have named all these reactions at these points. Now we need to find one of these reactions, and one of the questions says that we have to find the internal loading at the point G, which is here, and a point H, which is at that point, right? You can see in the main figure this point is H, and that one's G. G has been written, and that is H. So just write it down. Oh, not that is not H. H is here, and that's G. I think there's something wrong with this dimensions. Okay, there is one more reaction which is acting at this point, which is by the hydraulic piston. So this is also a reaction. You just write it R of C, right? And this angle is 75 degrees. Okay, so we went through the first step of our set of steps, and the first step was to draw the reaction forces. We drew the free body diagram. Sorry, the first step was to draw the free body diagram, and we have a free body diagram here. The second step is, of course, to analyze which part of bar we need, where we need to put the what do you call that? The section. Where would you make the section at the point of the bar? So G is where we need to calculate in the first question. So we will basically make a cut at that point in the bar. Now the second thing we need to analyze is what portion of the bar we must consider. Okay, so we should consider basically the right hand side, because we do not know the forces acting at this point, but we definitely know. So now we'll go ahead and calculate the values for NF. Okay, and that will be a straightforward thing to do, because we will consider this bar, which is in this direction. Okay, and the moment is acting at this point, so there has to be a moment which will negate this motion, which should be acting in the other direction, and this moment will be generated by NF. So we will form it into an equation. So this is the equation, NF multiplied by 3. So NF will be acting in this direction. This distance is 0.3, and then there will be 600 into 9.8, because this is kg, you got to convert that into newtons and multiply that by 0.5, which is this distance here, 0.5. So when you do that, and one more thing to notice is this moment at that point will be in the clockwise direction, and therefore that will be positive. So we have a positive, and at the end you see you know NF is acting on the negative x direction, but we did not give any sign here, and at the end we got a negative value for NF, which is correct.